This feedback mechanism can be found in multicell or supercell storms which occur mainly over large land masses in summer. They require the following conditions: a great depth of instability with sufficient moisture, strong vertical wind shear, and a stable layer between warm air at low level and cooler air aloft. We can see two of these requirements on this diagram. There's a great instability through this part of the atmosphere and a slight temperature inversion here, which helps initially to gather energy at low levels. As the daytime temperature rises, this inversion is broken, releasing energy to higher levels. Wind shear is also required to maintain cloud development. This is often achieved across the UK in this synoptic situation. Note the cooler, drier air at 400 hectopascals coming from a more westerly direction. This overlies air coming from a more southerly track, which is warm and moist. The directional difference between these two flows gives the wind shear. The surface flow is often southeasterly, again adding to the wind shear. The supercell system will usually start with an initial stage in which some instability is released at medium levels in the troposphere. This is typified by the appearance of altocumulus castellanus. However, the great depth of instability is only released when the slight inversion is broken, usually by daytime heating. Dramatic and vigorous ascent then takes place, with a cumulonimbus cloud quickly forming. The key to the continued development of this type of system is that the downdrafts are offset to one side because of the wind shear. In this manner, upcurrents carry on maintaining the cloud, and the downdrafts continue to produce the precipitation, gust fronts, microbursts, etc. The movement and development of supercells depend upon the winds that feed into the individual system. The direction of the outflow sometimes coincides with the inflow, or low-level winds, to produce convergence in certain areas. This convergence then creates uplift and another cumulonimbus cloud development. These are called mother and daughter cells because of the way one spawns from the other. Forecasting thunderstorms is largely a matter of matching the conditions necessary for the storms with the trigger mechanisms using computer-generated products and observational data. Satellite imagery and radar are then used to detect and follow the development of the storms. The aviation authorities have produced guidelines on avoidance distances. Here is a table showing recommended distances from cumulonimbus activity. Pre-flight briefing is particularly crucial in weather where strong convection is expected. Low-level significant weather charts as well as TAFs should give a good indication for timings and location of cumulonimbus development. Use of onboard radar, as well as visual clues obtained by looking out of the cockpit, will also greatly add to flight safety in such conditions. We're now going to discuss the hazards associated with cumulonimbus and thunderstorm development. Here are the main hazards. Select 1. Turbulence. Severe turbulence can occur in and around cumulonimbus clouds. Particularly during takeoff and landing, turbulence underneath a cumulonimbus can be very significant and lead to overstressing of the airframe. Articles can be thrown around in the cabin, and pressure instruments may experience lag and give false readings. Icing. Severe icing can occur in cumulonimbus clouds between 0 and minus 45 degrees Celsius, but can be particularly significant in the range -3 to -10 degrees Celsius. High concentrations of large, supercooled water droplets can lead to severe clear icing on the airframe very quickly indeed. Carburetor icing can occur at temperatures between -10 and +30 degrees Celsius. Hail. Hail can be encountered at any height in and underneath a cumulonimbus cloud. It can also be experienced beneath the anvil outside the cloud. Severe damage can be caused to the skin of the airframe. Lightning. Lightning is most likely to occur within 5,000 feet or 1,700 meters of the freezing level, in a part of the cloud that usually has a temperature between +20 and -10 degrees Celsius. If lightning is within the vicinity, expect the following effects. The pilot can be temporarily blinded. The compass may need to be re-swung. The ADF can become unreliable and point into the storm. If the airframe is struck, then skin damage may be evident. Pressure variations. Large pressure variations can occur in and around cumulonimbus clouds. Changes to the QNH, or QFE, can lead to errors in the indicated height of ±1,000 feet, or ±300 meters. These, together with severe turbulence and strong winds, can give very dangerous conditions near the ground. Microbursts. Strong downdrafts of relatively cold, dense air can descend from quite high levels within a cumulonimbus cloud at speeds in excess of 1,000 feet per minute, and in extreme cases of 6,000 feet per minute. Where the air is concentrated in a small area, it's known as a micro or macro burst. Usually these involve rain or hail falling as well, but not always. As the air hits the ground, it spreads out and moves away from the cloud at speeds of up to 50 knots horizontally. An aircraft on approach or takeoff can experience the following effects. Strong headwinds at this stage causing an increase in performance and airspeed. As a result, the pilot will reduce power to maintain the speed and lower the nose to recapture the glide path. However, if the aircraft continued to this stage, it would be exposed to massive downdrafts. Now the aircraft has very low power settings, a decaying airspeed, and massive loss of lift. Lastly, at this point, the aircraft has tailwinds which will significantly reduce the performance and possibly cause the aircraft to contact the ground prior to reaching the runway. Microbursts are usually restricted to within an area of 3 nautical miles, or 5 kilometers, of the cloud. Any greater, and they are called macrobursts. A warning sign of their existence is virga, or dark streaks of precipitation falling from beneath the cloud, but not reaching the ground. Microbursts are most commonly found in association with summer air mass thunderstorms, where surface conditions are dry. It's important to note that microbursts can, on occasion, be found under benign cumulus clouds. Water ingestion. If the speed of updrafts approaches or exceeds the terminal velocity of falling raindrops, the resulting high concentrations of water can cause problems for turbine engines due to water ingestion. The result may be engine flameout, or structural failure in extreme cases. Tornadoes. Tornadoes are usually associated with severe thunderstorms or tropical revolving storms, particularly those found in the Midwest of the United States. Wind speeds within tornadoes can exceed 200 knots, and the diameter of the vortex is typically less than 300 meters, with an average of 100 meters. We shall look at these phenomena in more detail later.